Before you can really start to analyze circuits as a whole, there's a few things we're going to have to understand, and one of the most important of these concepts is what's known as resistance. The purpose of this video will be to help you answer three questions. The first being, what exactly is resistance, specifically as it pertains to a circuit? The second being, what are the four factors that affect the resistance of a material or of an object? So how can you actually affect how much resistance or how little resistance you can generate? And the last question would be, what are the units of resistance? What's the variable? What do we measure it in? So we can start to actually analyze some problems related to this. Most of this video will pertain to these four factors that affect resistance. We'll take a look at the units and the variables associated with resistance in more detail when we look at circuits. But for right now, we're going to focus on these three questions, and these are three questions you should be able to answer at the end of this video. So to start with the very first one, what exactly is resistance? Well, if you just think about it as the term that it is, most of you can probably figure out that resistance essentially just means opposition. It's the opposition to something. The way we're going to deal with it within circuits and electricity is we're going to define resistance as the opposition to the flow of current. And of course, current is just electrons that are moving throughout a wire or a circuit or an appliance, some kind of electronic device, which we've discussed previously. So as opposed to static electricity, where these electrons will just stay in place once they are transferred, current is the flow of electrons through a circuit, and resistance is anything that opposes the flow of that current. So anything that slows the current down is going to be known as resistance. And anything that you essentially plug into an outlet or that runs off of a battery or some kind of power supply will generate resistance. So your refrigerator in the kitchen, that is going to slow down the current. It's going to steal some kinetic energy, some electric potential energy from those charges, and it's going to convert that to, in that case, heat or a lack thereof. We haven't really dealt with heat exclusively. If you plug in a fan, it will convert some of that energy into kinetic energy as the fan blades spin around. But essentially resistance, anything that's going to slow this current and then use that energy for some other means, some other useful purpose. So things like lamps, refrigerators, laptops. If you plug your cell phone in, you're charging your cell phone, computers, televisions, anything that you essentially plug into an outlet is going to generate resistance. It's going to generally going to slow that current down as it passes through that device. And that's what the term resistance actually implies, and that's how we're going to use it moving forward. Now the next thing would be, what are the four factors that actually affect how much resistance a material or a specific appliance can generate? So if I plug in my refrigerator, it stands to reason that that's probably going to have more or less resistance than something else like maybe a can opener. It doesn't need nearly as much power to operate a can opener. So what is different between the refrigerator and the can opener, or television and a cell phone charger? So what are these four factors that actually affect the resistance of a material or an object? And to start, or to relate that to you, I'm going to compare it with an analogy. All right, so instead of the resistance of current traveling through a circuit, we're going to look at the resistance of somebody trying to walk down the hallway. If it's a nice clear hallway, it should be easy to get down, but that's not always the case. So if we take a look here, I want to look at two examples. I want to take a look, this is the hallway. We have a top view, and we have a top view of a second hallway. You're trying to get down the hallway in either case, but if you've noticed, particularly between classes, there's always these annoying groups of students that either walk as slow as they possibly can, or they decide that right about here, right here, they decide they're going to have the, I don't know, most groundbreaking conversation, and it's so important that it doesn't matter if anyone else needs to get by. As you can see, I'm not bitter about this in any way whatsoever, but essentially you'll notice they form these little pockets. And if you want to get down the hall, they're really annoying, but you kind of can find your way around them. If there's not that many groups, you can still get through. And it doesn't take that much time. There's certainly some resistance to you trying to walk down this hallway, but you can still get through. It's just annoying at the end of the day. Now, if we look at the same hallway, but there is an even higher number of these students that just tend to populate around and talk about, I don't know, ridiculous things that you guys talk about, you can still get through, but now there's a little bit more resistance. So you have to try and find whatever opportunities you can to get through there. So it's the same situation. We have some students just kind of clogging up the hallway, but in these two different cases, I have significantly more students here. So hopefully that's pretty clear to see. It's easier to get through a hallway that doesn't have all these students filling it up. The exact same thing occurs in a circuit. But instead of talking about students or maybe gossiping in the hallway, we're talking about different types of material. So whereas iron molecules have a different structure than copper molecules, and we're not talking about you trying to walk down a hallway full of students, it's an electron trying to get down through that wire, but it has some obstacles in its way. It actually has these molecules, in this case iron molecules, in this case copper molecules. And the electron in either case can still get through, but you'll notice that in a case of iron, in this case, which has a different structural arrangement, well, it's a little bit easier for these electrons to get through in copper. There's a little bit more space, the molecules aren't as large, and it just comes down to the structure of the material. All right, so the molecules and their structure. That's the first thing that's going to affect the resistance. And it kind of makes sense. The less room there is to move because of the structure of the molecules, the more room, the easier it will be able to get through, the less room, the harder it will be to get through. So molecular structure is one of the things, just the actual material type you choose. Some of them will naturally generate more resistance, and some will naturally generate less resistance. All right. A second characteristic, or a second example, going back to walking down a hallway. This one's a little bit more straightforward. I could ask you to walk down a short hallway, and you'll get through pretty quick. If I asked you to walk down a hallway that maybe was twice as long, you can still get through, but you're going to be taking a little bit longer. You're going to go a little bit, maybe slower is not the best word. Let's say longer. It's going to take you a little bit longer to get down because you have this extra distance to try and cover. So the second, outside of molecular structure, is actually the length. All right, the longer of a wire you have, the longer the circuit is, the more resistance, because all these wires, to some extent, have some kind of molecules in them that are going to slow that down. If you have a longer wire as opposed to a shorter wire, you're going to have more obstacles you may bump into. So the length of a material will also affect its resistance. So far we've discussed the fact that molecular structure will have an effect, but so will length. The length of the resistance, or the length of the path which the electrons have to travel through, will also have some kind of impact. Now to show you that in terms of a circuit, here again I have two wires. You see that they're made of the same material because they generally have the same structure, but I have a short wire and a long wire. Again, these electrons, they do the best they can to get through. And just from taking a look, even though it's the same material, you can hopefully see here that because I have a longer material or a longer wire, it's going to take a little bit longer. So in this case, I'd have lower resistance in a shorter wire, and I'd have higher resistance in a longer wire. And that just has to do with, again, with the obstacles that are in the way. If it's a longer wire, you'll have more of these structural obstacles to try and get around. So the length of the resistor as well as the material type are two things that we've discussed so far that will affect the resistance. So if we have a long wire, high resistance, short wire, low resistance. If we go back to the hallway example, and I want to take a look at the third characteristic. I apologize if this guy isn't running. You may not have noticed that, but it bothers me. But I drew that leg the wrong way, and we're just going to deal with it. So here we have two side views of a hallway. Here's the front view looking from the front. I have a very wide open hallway, a high cross-sectional area, and I have a smaller hallway with a smaller cross-sectional area. You should be able to notice that right here, you can pretty easily walk right through this hallway, whereas in this case over here, you're actually going to have to probably get down and crawl because this cross-sectional area is so much smaller. So if you imagine trying to walk or run down a hallway, and then walk or run down a hallway that's essentially a small tunnel, it's going to take you longer to get through something that has this smaller cross-sectional area than it is when you can just walk right through. So the third characteristic is what's known as cross-sectional area. If you think about it, it kind of makes sense as well. The more area you have to try and get through, well then every time you run into an obstacle, all right, let's say there's a few obstacles in either of these, you can just tell there's more space when you have more cross-sectional area to try and get around these obstacles. Whereas in a smaller cross-sectional area, there are not nearly as many opportunities to easily get around these molecules. So the cross-sectional area of a resistor will also have an impact. And again, to show you that in terms of a circuit, I have two wires of the same material, but the electrons, anytime they run into an obstacle, as here, well, they have the option. Well, I could probably go around here. Oop, let me go here. Anytime you run into an obstacle, the electron has a pretty wide range of possibilities to get around it, whereas in a very thin cross-sectional area, there's really not quite as much room to try and get around, so it's a little bit harder for these electrons to try and get through. So if you have a wide cross-sectional area, you have very low resistance or lower resistance. If I have a much thinner cross-sectional area, I generally have a higher resistance because there's not nearly as many paths to get through. Just like if you were walking down a hallway again, it would be significantly easier than if you had to crawl the same length down a very small cross-sectional area tunnel. There's just less opportunities to try and get around whatever obstacles present themselves. The last one, a little bit tricky, but that's only because we haven't really discussed temperature. But if you think back to chemistry, hopefully you remember that temperature is just the kinetic energy of the molecules. All molecules vibrate, even in a solid. But if we go to the hallway example, let's imagine you want to get from point A to point B, and you have some students in the hallway, and they're just kind of walking randomly back and forth. You can kind of predict where they're going to be, and you can adjust accordingly. And if they're only walking, it's probably fairly easy to try and get through them, just to make sure you don't bump into too many. If you take a look at the same hallway, but now these students are running back and forth, I have no idea why, but assume they're just running all over the hallway. If you're trying to get by, you really have to make sure that you don't bump or crash into any of these students that are running in all different directions at all different speeds. It's going to take you a little bit longer because you really have to, you're going to wind up bumping into so many more students, and that's going to slow you down. Similarly, if we take a look at the resistance in a circuit, the electrons are essentially doing the same thing. But in a very cold wire, these molecules are vibrating, but they're not vibrating very much. So this molecule right here is only taking up this much space because it's only vibrating a short amount. Since these aren't really vibrating back and forth violently, the electron has much more room to try and get around without bumping into any. So in this case, you have a lower resistance. All right, so a lower temperature means lower resistance because as you go through, they're not vibrating nearly as much as they are in higher temperatures, so there's much more room to try and get around them. The odds of bumping into a molecule that's vibrating is much lower. If you heat that wire up or you heat that resistor up, the same molecules will vibrate significantly more. So now they're taking up more room as they vibrate back and forth. So the odds of one of these electrons kind of bumping into one as it goes through is significantly higher, and it's going to take much longer for this electron to travel through. So a higher temperature will give you a higher resistance. Again, it just has to all do with the amount of space the electron essentially has to try and pass through. The last thing I wanted to talk about, we've talked about what resistance is, we've talked about what those four factors are. If you don't remember, we were talking about the length. So the longer the wire, the higher the resistance. And the shorter, then the lower the resistance. All right, and that just has to do with how many obstacles you have to try and get through. The longer, the more obstacles you have, the higher the resistance. The shorter, then you have lower because there's not nearly as many obstacles in your way. We also have temperature, which we just discussed. The higher the temperature, the higher the resistance. The lower the temperature, the lower the resistance. And that has to do with the fact that these molecules are vibrating either violently back and forth, and it's much harder to get past them, or they're vibrating not nearly as much. And it's a little bit easier to try and get around without bumping into them. Molecular structure, or the material type. Some materials just generally don't have as much space for these electrons to travel through, and that makes a higher resistive material. Molecules that have a little bit more room, things like copper, they tend to have a lower resistance because these electrons can kind of jump around very easily. And the last one we were talking about, cross-sectional area. All right, well, think of that like a hallway again versus a tunnel. Wide open hallway, you can walk right through. If you have to crawl through a tunnel, since it's so much more of a confining space, it's going to take you a little bit longer. Going back to the whole length molecular structure, the cross-sectional area is smaller, there's not as much room to try and get around these obstacles. It's like if I placed, I don't know, 10 desks in a hallway and said walk down the hallway, probably wouldn't take very long. But if I took 10 chairs and I just kind of shoved them into this small tunnel and I said, go ahead, get through here now, it's still the same length, there's still only 10 chairs, you're going to have a much harder time. So smaller cross-sectional area is higher resistance, a wider open, higher cross-sectional area, less resistance, a little bit easier to get through. Right, and the last one at the end of the day would be what exactly do we define resistance as and how do we measure it? Well, it's nice and easy. Resistance is represented by a capital R, and it's measured in a unit that we refer to as ohms, O-H-M-S. And it's represented by like this little upside down horseshoe. So as an example, if a circuit showed you a diagram like this is showing you that it is a 5 ohm resistor. 5 is a fairly low number, so a 5 ohm resistor has less resistance than our second example, which would be a 200 ohm resistor. This just shows you that it has more resistance. So you'll see this symbol a lot. Just understand that it measures resistance. It's known as an ohm. And at the end of the day, if you see a capital R, that just stands for the resistance, the amount that this material